Okay. Lost my mouse or what? Hold on one second. Probably lost my mouse. Well, I lost my left click. This is weird. Oh, anyway. Seems it comes back. All right, let's continue here. So today we're going to continue our AC small signal analysis, which, remember, inevitably including the DC analysis. Okay. So DC analysis always goes first. We have a procedure for that in previous lecture. So remember, have it as one of your handouts during the exam. By the way, today we're going to review the midterm 2, okay, by the second half of the lecture. Okay. Here, let's quickly go over this procedure once again. Okay, so it has basically 3 steps, okay, 3 checks. First step is calculate the small signal model parameters, 2 parameters. Okay. We have 2 formulas. Okay, they are available in the lecture slides 14, not lecture 14, but lecture slides 14. Okay, they are different. Okay, they're different. Page 6. 2 formulas for 2 model parameters, GM and R0. By the way, what does the GM mean? I mean, this parameter is called what? What's the name for it? Anyone remember? GM is called what? Anyone remember? What is GM? What is it? R0. And also, what is R0? R0 is what? Good, good. Kevin is right. Okay, GM is called transconductance. R0 is what? What is R0?
It's the resistance between the drain and the source.
Very good, very good. Okay, it is called output resistance. However, I agree with Daniel more, okay, because his definition is actually more meaningful. In other words, this output R0 is always between drain and the source, okay, no matter what, always between drain and the source. Has nothing to do with where is the ground, has nothing to do with where is the output. So I agree with this definition much, much more actually. Okay, it's always between the drain and the source. So it's the resistance between drain and source. Perfect. Great job. A great answer. Okay, so knowing these 2 things, once again, you need these 2 formulas. Okay, this is the first step. Second step is find the correct small signal AC circuit. So first, you remove all of DC sources and short all of the capacitors. You might come across 2 types of capacitor. One is called bypass. The other is called coupling. Okay, if you see what is mean by coupling, what does it mean by coupling? Okay. And what does it mean by coupling, and what does it mean by bypass? Okay, 2 types of capacitor, if you see. Okay. And then you need to place the small signal model for the MOSFET transistor itself right in the middle of your paper. Be careful to identify is N channel or P channel, right? Because we have 2 different small signal model. Okay. And the model is available as same place with these two formulas. Okay. And then you extending the circuit terminal by terminal, okay. Gate, source, drain, okay, following certain order to extending the circuit one terminal after another, based on the given circuit. Okay. Based on the given circuit. Don't try to remember anything. Don't try to memorize anything. Okay. The given circuit might be different. Okay. Maybe just a little bit different. If you try to memorize something, you definitely gonna make some mistakes. It's not based on the memorizing. It's based on the given circuit, which is varies. It's varying from one problem to another. The third step is obtaining the gain. So this is pretty much telling you the goal, or say the only goal for the small signal analysis is to find the gain, the AC voltage gain, A sub V. And here is pretty much a arsenal. Okay, this is pretty much a arsenal, full of weapons, full of equations for you to analyze the circuit. Okay. Circuit. In the last lecture, we have done two types of common circuit, common source, and a common drain. Right? Today we are taking care of the third one. Okay? It's common gate. Common gate. Look at this given circuit. The input is VI, AC input. They're going into where? Going into source, right? So the input is source. Output here is what? Is the drain, right? And that's why this is a common gate. That's why this is a common gate. So try to follow the same procedure to come up with, first of all, the AC small circuit. Of course, assuming we have done the two parameters calculation. Okay, assuming we have done those two parameters, GM and R naught. After that, now go ahead to find out the small signal circuit for this given circuit. I will give you guys 3 to 4 minutes to try this out. Okay. And if any questions, you can immediately bring it up. Okay, I'm still available. All right, carry on. All right, let's take a look at this, the resultant circuit together, and try to find the equivalent, of course, equivalent small signal circuit. Okay, small signal circuit. They're doing nothing but following the given procedure. Okay, and once again, do not try to memorize anything. It won't work. It won't work. All right. So first of all, you're seeing 2 voltage source, right? 2 voltage supply, 2 power supply, 2 DCs, B minus and B plus. Obviously, they both gonna short it to ground. They both gonna short it to ground. And also, we are seeing this is the current source, right? DC current source IQ, DC current source IQ. We don't need to kind of struggle with how we come up with this current source. Okay, not in this class. In 358, you learn what is meant by a current source here. And anyways, to this DC current source, what we do?
Open it.
Open it. That's right. So open here. Here becomes ground when meaningless then. Right. So here is open. Here is ground. Okay. This is how to deal with DC source. Next, we have 2 coupling capacitors. What does it mean by coupling capacitor? We have an input side capacitor series connected with the AC input source. So this is the input AC coupling capacitor. C sub C. See, the subscript makes perfect sense. And also we have output, the second coupling capacitor, series connected with the output voltage here. So output terminal here. So it's output coupling capacitor. Right? Short both, right? Short both is what we should do according to the given procedure here. Okay? So after this, we're gonna do what? Place the small signal model of the transistor right in the middle of the paper, right? So this is the N channel or P channel? What is it?
N channel.
It's N channel, right? So N channel, I start to plot. N channel, if this is something, again, you don't need to memorize because it is on your cheat sheet, right? You're just copy and paste. Okay, I'm serious on this. Don't try to memorize it. It's wasting time. Gate, source, and drain. And of course, we know this VGS times GM. And here is VGS. This is the transistor and the transistor itself. Of course, according to the requirement of the problem, we decide to involve that R0 or not. Okay. Be very careful. R0 is equals to VA divided by ID, right? According to ID, according to VA here. According to VA here, if the VA is infinity, then R0 is infinity, which means open circuit. So, which means further means you don't need to involve this R0. Right? If VA is finite, that means you need to involve this finite R0 as well. Okay, it's all depending on the given, okay, or depending on the VA given value. So this is how we take care of the small signal model of the transistor. Next, I'm using the black color to extending the circuit terminal by terminal. Okay, terminal by terminal. We can begin with, because here, if you look at here, this is source, right? This is source. So let's begin with source. Be very careful. Once again, you need to know we are extending source. Source means here. Okay, it's not about look. It's about the real location of each terminal. We are talking about a source. We are going to here. So according to the given circuit, here is open circuit. We don't need to worry about it anymore. Okay, we just discussed. So the source connect to where? Shorted capacitor. Okay, and then connect to what? RSI, right? The source down here connect to RSI. The other terminal of RSI connect to the positive polarity of the VI. And the other terminal, negative terminal of the VI is the ground. Looks weird. Okay. since we haven't, maybe this is our first time to see a circuit looks like this, but it is correct. Okay. Don't let your feeling mess you up. Okay. You're following the rules, then nothing wrong. It's about the feeling. Okay. Then we are done about the source. Makes sense. Next, let's take care of the drain. Drain is the other side, output side. Okay, the other side. The drain is connect to what? The CC2 is shorted, so drain connect to RD and RL. And what is the relationship between the RD and RL?
Parallel.
Parallel. Okay, very clear parallel. The parallel between what? Between the ground down here and the drain up here. Does it make sense? So the drain connect to, all right, RD, parallel was RL. And also, don't forget, the drain is the output. Drain is the output. And the ground, feel free to short with this ground together. Okay. Does it make sense so far? If so, we are done with the drain. The only thing left is the gate. So what gate is connected to? Anyone knows? Gate connect to where?
Just ground.
Very good. Yeah, the Shane is correct. The gate connect to the ground. And besides of Shane, anyone knows why is ground? Why? Anyone? Yeah.
Is it because the capacitor gets shorted, so it just takes that path?
Exactly. Very good. Very good. Okay. The gate is what? Ground directly. No matter you like it or not. Here we go. The reason is, as Daniel just mentioned, this capacitor is short, right? Remember, we treat all of the capacitor, no matter what, capacitor as short circuit in 318, this class at least, right? So if this is short, what happened? Your short path is parallel, exactly parallel with RG. What happened then? No current going to flow through RG. No current. No current flows through RG. RG is open circuit. Zero current, open circuit. Right? Therefore, the gate is directly go through the shorted CG to the ground. So what does the CG called? What kind of a capacitor this is? Bypass. Okay, we remember we mentioned two types of capacitor, coupling and bypass. And here is the bypass. Okay. The name is very meaningful, right? It says very informative. It's very informative. It's telling you it's bypassing. Bypassing whom? Bypassing whatever parallel with it, which is RG. Right? That's why gate is directly ground. Okay. All right, take a look at this resulted small signal circuit to see any questions. Is it okay? Because you can easily imagine you're gonna do this. You're gonna need to do this in the midterm too. Okay, so make sure you know how to do it. Okay. This is the small signal circuit. And if this is fine, then and here is the solution provided by the textbook. And can you guys how this result, how this circuit, how this one is equivalent to whatever I gave? Can you tell how they are equivalent? Let me present my once again here. Compare this to. Does it make sense? They're same, equivalent. This part is easy to understand, right? This part is easy. Same as this part, right? Blocking the screen, right? It's okay. Shrink it better. So once again, this part is easy to understand, right? Same as here. Now, how about this dependent current source? What happened to it? Basically, you drag this source node, drag it, right? Drag it. So make the source and the drain along the same horizontal line. That's how you end up with here. Does it make sense? Of course, the dependent current source current is towards left. Same here, it's going down. And the gate itself is open circuit with respect to the source. And the gate is just a ground, so your here is not plotting any gates in connection at all. It's just the gate is just a ground. It's just named the ground as gates. That's all. Makes perfect sense. And RSI and VI just drag them to align with the horizontal line as well. That's how the circuit end up with this way. Okay. So the key is how you judge if the circuits are equivalent or not. It's not about look, absolutely not. Okay. Never be, actually. Never be. Look. It's always about the connection. It's always about the connection. Any questions here? Seeing Kevin here, they, all right. Any other questions? Any concerns here? Does it make perfect sense? And of course, in the exam, you don't need to worry about which version of answer is considered as correct. Okay, I won't care about the look. I'm checking your circuit by checking the connection, terminal by terminal. As long as the connection is correct, I don't care what the look is. Okay. So don't worry about that. You might have different look, completely different look. However, it's not necessarily wrong. It's about the connection. It's not about look. Speak, Kevin. I'm seeing you're typing something. What is it?
I'm just taking a note to maybe ask later. I'm not sure yet.
Oh,
so I don't forget the question.
Okay. All right. If this is fine, then if this circuit is fine, then let's go ahead, try to come up with some equations. And to do that, let me present this arsenal and this circuit here. And this circuit here. Okay, you have arsenal and the circuit here. Give you guys another kind of 3 or 4 minutes. Try to come up with the equation yourself. Go ahead. And then you need to count, right? The number of equations and number of unknowns to see if they're good. Try to write the equations yourself. Obviously, the output equation is fairly easy, right? We have been doing that for at least twice. And then you need to somehow link the VGS and the VI. Hopefully, that's not very difficult either. Or we can write it together, actually. So first output equation, right? The first idea is the output equation. The output equation is fairly easy, isn't it? Negative GM VGS times RD parallel with RL. Negative sign need to be there because current flows through RD and parallel with RL is upward, right? Upward, introducing voltage with such polarity. So this polarity is opposite to the polarity of V naught. So you need to have a negative sign in front. Right? This is the output equation. Next equation, we're trying to link the VI, which is here, with our VGS. This is the idea. Okay, this is the idea. Look at the second weapon here. The relation between the VS and the VGS. Okay, this is a pretty much meaning how you link the VI or VS, whatever is given, to VGS or VSG, okay, or VSG. So how to do that? I think the easiest way just this KVL. How about that? So inside of this KVL, you have three voltages, right? VGS, the voltage cross RSI, and the VI. So if you write this KVL as simple as this, right? RSI plus VI equals 0, right? Very easy. Of course, VRSI need to be further substituted by something related to VGS or VI, right? So how to find the voltage across the RSI? What's the idea? Anyone knows?
Wouldn't you use the dependent source with Ohm's law?
Very good. By Ohm's law. Very good. Okay, Josh is right. They're using Ohm's law of RSI. So pretty much you are using the current times resistance. And then what is the current then? As Josh mentioned, they're using dependent current source. What is it? GM VGS. Does it make sense? In other words, the current flows through the SI is nothing but GM times VGS. Does it make sense? Because here is open. There's no current here. All of the current here flow down through RSI, which is also the current of VI, believe it or not. Right? And if this equation makes sense, we can count how many unknowns. 1, 2, right? 3 unknowns, 2 equations. What do we do? Or say, what do we say? Is it good or not?
It's good.
It's good. It's good. Enough. 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 Look at here. Number of equations equals number of unknowns minus 1. Yeah, it is the case. It is the case here. So we're ready to conduct algebra. Does everything make sense so far? Any questions? Of course, here, the textbook providing the solution in such way, which is okay. From this circuit, it's deriving 2 equations. If you read through carefully, you will see they are exactly the same 2 equations. Okay? The same 2 equations. No difference. Actually, no difference. Okay. So take a look to see any questions. Yeah. If all good, let's do some summary here. Okay, what do you mean by summary? Summary means a summary about the MOSFET amplifier circuit. We have up to 3 types: common source, common drain, and common gate. And we are summarizing them from 3 aspects. First, regard the gain. Second, regard the input resistance. Third is regard the output resistance. Okay. First, the gain. Common source has decent gain. It has decent gain. It's greater than 1. It's not very big, but it's greater than 1, which means common source is able to amplify, right? Able to amplify the input signal. The second, common drain. Can common drain amplify? No, right? Common drain is basically do nothing about the amplification. Does it make sense? Not much gain. A gain of 1 for what? Not for amplification, at least. Okay. Common gates is able to do amplification as well. But this gain, I can tell you, is less than the common source. It's in terms of gain. Second aspect, in terms of input resistance. By the way, input and output resistance are very important. If you recall the concept back in module 0, to voltage amplifier, we are expecting a high input or low input resistance. Which one we like? High or low? The input resistance. Anyone still remember? And why?
High, so there's more voltage drop across it.
Very good. Okay. Kevin's answer, including the answer as well as the reason. Okay. It's called loading effect. And loading effect to voltage divider means, to voltage amplifier means nothing but a voltage divider. The higher the input impedance, the more voltage your amplifier can receive from the source. Okay. Say this is the source. There's a source resistance, RS. Inevitable, okay. Two terminals feeding input resistance of amplifier. What do you see? The higher the Rin is, the more voltage the out of Vs going to be given or passed on to the amplifier, right? This is amplifier, right? So that's why the higher the better for input resistance of voltage amplifier. But to CS is equivalent resistance. It's all up to the design. It's all up to the design. Common drain is also, it's up to the design equivalent resistance. What does it mean by equivalent resistance? I will show you. I will show you momentarily. And the common gate, what do you see? Input resistance is what? Low, which means what? Common gate cannot be a input stage. Does it make sense? Your amplifier circuit system might include multiple stages. First stage is input stage, trying to take care of the input resistance, trying to make the input resistance big enough. So common gate can never be the input stage, right? Because the input resistance is very low. It's bad. The output resistance, what we want. The lower the better, right? The output is like what? The output of the amplifier this time, the feeding load, right? This is load. Now this guy is the amplifier, right? And it has output resistance here, series connected with the dependent voltage source. You generate this amount of voltage from your amplifier, and then need to be passed down to what? Load. Okay. So this time we care about how much voltage your load can receive. So the lower V naught, the better. Or say the lower V naught compared to RL, the more voltage your RL as load can receive from your amplifier. Does it make sense? So the lower the better. Okay, V naught is the lower the better. Who is a good one? Common drain is a good output stage for amplification system. Right? The lower the better, and common drain is good one. Common source, no, not that good. Common gate, not that good. Common drain is good. Now let's talk about input resistance. What does it mean by equivalent resistance? It's actually as simple as this. Okay. Remember, we have seen such topology of a circuit for amplifier and MOSFET amplifier quite a bit. So we call this R1 and R2, right? So the equivalent input resistance is what? R1 parallel with R2. Equivalent input resistance is R1 parallel with R2. So if you make R1 and R2 big enough, or say make their parallel big enough, that is equals to the input resistance here, which means you're able to design a big one. This is so-called equivalent resistance. Resistance. Here also reminding you again, and not try to memorize the formula. What does it mean by formula here? If this formula means, first of all, you have GM and R0, two formulas. You don't need to memorize them. They should be on your handout or cheat sheet to copy and paste. Right? What other formulas? Look at these results. Look at this result. This is a common gates gain. Don't try to memorize it, okay? Common gate amplifiers gain not necessarily equals to this. It's all up to the given specific circuit, particularly. Okay, so this result is meaningless. It's not representing the generic gain for common gate amplifier. It doesn't make any sense. Same thing here. The common drain, last lecture, and the common source, right? Common drain and common source. This is a common source. Is common source voltage gain follow this formula? No. No. Okay. This is the result for this particular circuit. Okay. Don't try to memorize these formula. No. They won't work. Okay. This result is the common drain voltage gain formula. No. Absolutely not. Does it make sense what I'm talking about here? Yes or no? Any response?
It makes sense.
All right. Thank you, Shane. And any questions? I'm seeing so long question. I'm too lazy to read your question. Can you speak out, Kevin? What is it?
Will we be given VA during the exam so that way we know if we need to ignore the R not? Or if it's not given, do we assume that means we can ignore R not?
No, the VA, first of all, will be definitely given. Okay. And by reading the given VA, you know that R not should be involved or not. VA will be definitely given. It's not something you need to find, or not something you need to guess, assume. No, VA definitely will be given. Sure. Any other questions or concerns? All right, if all good, then let's do a couple of DC analysis exercise. Okay, just pop up 2 ideas about the DC circuit. DC circuit only. So first of all, we are quite used to seeing such topology, right? Once again, in the homework as well as our lecture example, right? They basically all follow such topology. You might have a positive up voltage source, 5 or 15, it doesn't matter what is the value. We might have a negative voltage here or ground, that doesn't matter. And we are seeing R1, R2 like this. And we are seeing RD, RS like this, right? So we're quite used to such kind of a DC circuit. But the DC biasing could be implemented by other topology. Let me show you one. And then accordingly, we try to figure out how to conduct the DC analysis. Let's see. DC analysis exercise. Give you 2 new topologies. Get too used to it. Okay. First of all, we have there's no specified resistance value or supply value, but it doesn't matter. We're still able to come up with the equations. So I give you a couple of minutes for you to try to come up with the equations. Of course, the first equation we know is the saturation, right? Saturation. And also we can easily tell that this is what? N-channel, right? You can easily tell this is N-channel. So the first saturation current equation is definitely there. Number 1, equation 1, definitely there. Next, what we need? VGS KVL, right? The from top to bottom KVL, right? These are the weapons. For VGS KVL, what we need? VG, remember? So these are kind of hints for you to come up with further equations. And so now I give you guys 3 minutes. Try to figure out the rest of the equations. How to find VG, how to write that KVL, 2 KVLs. Of course, feel free to have the DC circuit first, because this is not exclusively DC circuit yet, right? You want to have a DC circuit, and from the DC circuit, you go ahead to have more equations. 3 minutes, go ahead. Right. See, this is a DC circuit, right? This is a DC circuit. So from here, they're trying to first of all find VG, and therefore to write a KVL in VGS loop. So VG is equals to what? Anyone can tell? VG equals to what? And then the VGS KVL will be like what? Right? And then the top to bottom KVL will be what? Right? Oh, very good. Okay, the Kevin got the correct answer. VG equals to VDD. Besides Kevin, anyone else know why VG equals to VDD?
Is it because there's no current across that gate?
Very good, very good, very good. Here's the reason. Okay, Shane is right. Okay. Why VDD equals to VG? Simply because I gate equals to 0. There's no current here. No current here means no current here. No current here means no voltage drop through R1. No voltage drop through here. Meaning what? Short circuit between VDD and VG. Short circuit between VDD and VG means what? VG equals to VDD then. Right? Or you can think in that way. The VIG here is 0, means what? This is an open circuit, right? This place is open. This place is open. Then again, there's no current flow through R1. No current means no voltage cross it. No voltage cross it, then no voltage difference between VDD and VG. So VG equals to VDD. Does that make sense?
So how do we know there's no current there?
How do we know the IG equals 0?
Yeah.
Oh, IG is equals to 0. That's one of our DC analysis methods. It's one of our equations we have been using quite a bit. Here, this is DC analysis flow here. This is a flow chart. You can see it here. Or if no memory on this, how about that? As I said, one for our handout, right? See here? You guys all remember ID equals to IS, right? Another equation is IG equals 0. It's one of our weapon in DC analysis. Remember, this is what? This is the arsenal for DC analysis. Today we're using the arsenal for AC analysis. We had another arsenal for DC analysis. This is one of your handout you need to print out for the midterm. IG is equals to 0. Your gate of your MOSFET is open circuit. Same thing happened in the AC analysis too, actually, right? And the gate is always open. Why is that? Because you see this AC small signal circuit. You see the gate is connecting nowhere. The gate is always open. Open circuit means no gate current. In AC as well, actually. So gate is always open. But open doesn't mean there's no voltage. Okay, the gate voltage VGS is quite critical in controlling the IV curve, and the DVGS is controlling the Q point. Any other questions?
About the cheat sheets, so to speak, you said you would give us a list of which ones we can print off, right?
Yes.
All right.
Yes, actually, that's part of the review of the midterm today. And yep, I'm gonna announce it today, right after today's lecture. Yeah. But the thing,
Right,
the thing is a little bit, because now we are doing a lot of in-class exercise, right? In all of these exercise, I'm leaving time for you guys to write equations yourself. To do that, I suppose you guys already have them printed out. Otherwise, how can you write equations? I'm a little bit surprised that you guys not doing that yet. I'm a little bit surprised, but as to this list, yes, I will do it. To make sure you know which one you can bring in to the exam. Any other questions? And then what is the VGS KBO then?
Would that be VGS equals VG minus RSID?
Yep, yeah, that's quite regular, right? And now you know the VG, then it's just equals to VGS plus the ID times RS. That's it, right? And then from top to bottom, KVO, this is VD equals to ID times RD plus RS plus VDS. Right, these are quite regular. You guys have been doing in the homework and in class as well. All right, one more exercise. Similarly, another circuit, DC circuit. How about this? I'll give you guys another 3 to 4 minutes to write equations for this guy. And now this time, and this is called R1. Right, so following the similar idea here, the DC circuit look like what? So open here once again. So we have RD, RS, and the ground. R1 here. Right. This is a DC circuit. And therefore, you have ID, once again, equation, N channel. That is still N channel. ID saturation equation. And second, this time, what is VG?
0.
0. Okay. For the same reason, right? Same reason. No current through R1, so no voltage potential between the gate and the ground. It's the gate, and then we have VG as KVL. So we have VG minus equals to VGS this time plus ID times RS. It's the same. Right? And from top to bottom, KVL is VDD equals to ID times RD plus RS plus VDS. Right? Of course, here we are all assuming we are not seeing any bypass capacitor, right? But say if you have a bypass capacitor, what do? In DC analysis, it doesn't matter, right? Open it. But in AC analysis, what? You don't have RS then. The source is directly shorted with the ground in AC. Does it make sense? Right, so any questions? Any questions regarding the knowledge before we talk about the review? Any questions? Everything's good? All right, if everything's good, then let's talk about our midterm. Midterm, first of all, find out the problem after the exam. Well, it's a little bit too late, but hopefully you won't have any. Midterm 2. First of all, about the time is in a week from today. It's Tuesday, next Tuesday, lecture time. Same time slot as midterm 1. Same time slot as midterm 1. This is the time. Second, we will have up to 4 problems. Problem 1 is the multiple choice. Multiple choice problem. And here you might have 10 questions, but with 1.5 points per question, or 15 questions, but 1 point per question. Okay. Either or. So this is the multiple choice. Problem 2 is given circuit. Of course, MOSFET circuit. MOSFET circuit. You need to answer, first of all, identify the terminals, GDS. Second, identify the type, N channel or P channel. 3, identify is common what? Common circuit. 3 identifications. You need to answer these questions. And then you need to find the DC circuit. And then you need to find small signal circuit.
So would that question there include the equations or just the diagrams for the circuits?
No, very good question. Okay, so basically, these three are clear, right? These three are clear, right? As to these two, then remember clearly, okay? No equations. Therefore, no algebra calculations either. Only circuit. Only circuit. Don't waste your time on equations or calculations. No credit. No credit. And also, if you are writing equations for this problem, and even the calculations, if they're right, you're not receiving any points. If they're wrong, you are losing points. Did I make myself clear?
Yeah, so we're just identifying those first three. Don't worry about steps 4 and 5 necessarily.
Say that again.
So we're just worried about identifying steps 1 through 3 mostly, and then 4 and 5 if needed.
No. You need to take care of all of the 5 problems, 5 questions. DC circuit is asking for the circuit and the circuit only.
Oh, gotcha. Okay. Yep.
You need a circuit. You don't need to do anything further. That's what does it mean. You only answered question 1 through 3, ignoring question 4 and 5? No, you can't do that. Well, except you don't care about losing points.
So would that question be worded clearly enough that we know that this is the one we don't have to do equations for?
If you label that, saying
Like
no
equations.
equations, no. And also, I'm telling you, this is a problem too.
Okay.
You can pretty much memorize that because I'm not planning to change, the order of the problem. Problem 2, no equations, no calculations. Because I have a pattern here. And problem 3, guess what? You need what? Equations, but no calculations. Problem 4, what is it? You tell me.
Equations and calculations.
Say that again?
Equations and calculations.
Very good. Josh
Okay,
got the
okay.
pattern. Okay,
Clear.
Josh got the pattern. Are you following, Daniel?
Yep, I get it. I just wanted to
All right.
make sure like it would be labeled clearly enough, but I get what you're going for.
Because the question is asking, find the circuit. Find the circuit. It's not asking find the equations. It's not asking find the ID, yes, find and the VDS. No, it's
Right.
not
It's not asking for a value or anything.
exactly. Yep.
All right, I got it.
Yep. Find the circuit means find the circuit. Of course, if you do write those equations and even calculations, once again, if they are right, you just lose some time. However, if they're wrong, you're losing time and a point, which I can never understand why you are doing so. Okay. Problem 3, as I said, once again, this given MOSFET circuit. Okay, given MOSFET circuit. What you need to do is read problem carefully, read the question carefully. You have, again, multiple questions down below. And this time, you probably identify terminals, identify channel, identify common circuit. Okay. Or maybe just identify 1 or 2 out of these 3, because we just learned 3 types of identifications, right? So that's the question 1, maybe 2, or maybe 3. ID. Regular ID. The following question is find a DC circuit. And then the next question is conduct DC analysis. And then following, find the AC small signal circuit, or say small signal circuit. And then following that, conduct AC analysis, or say the small signal analysis. You need to conduct analysis. What does it mean by conduct analysis? Equations. Okay, I'm labeling that too. So read the question carefully. I'm asking you to do the equations only. No calculations. No results needed. As Josh mentioned, the pattern is to problem 4. Question 1, 2, 3 maybe again IDs. It's all depending on the given problem. Okay, you read the problem and the questions carefully. Okay, it's all up to your read carefully. And then what do you need to do next? Okay. So you need DC circuit and DC analysis. To find values for different variables, voltage or current. Next is what? Small signal circuit and small signal analysis to find what? Gain. So this is what? This problem pretty much means what? Equations and calculations. Does everything make sense? Let's take a look to see, does everything make sense? You know what you're expecting, okay? So in this exam, you pretty much not wasting too much. Okay? Just focus on answering the questions. Read carefully, okay? Read the problem carefully. All right, if no question, thank you for attending today's lecture, and talk to you guys on Thursday then. All right, thank you. Bye-bye now.